All right, guys, can you mute yourself, please? Don't want there to be uninterrupted stuff in between. So let's get started. It's now 10:50. Whoever is around is around. Whoever is not around, well, they have to catch up as usual. So today is probably the last lesson I'll see you, yeah, because next week is already your exam season. So I might or might not see you next week, all right? In terms of separation techniques, so you can actually turn off your video is fine so that you can save more data because if you turn on your video, it's actually gonna eat more of your data. All right. So let's get started. I'll get started on the qualitative analysis actually because that thing is quite tricky. So you know these particular type of questions, yeah. So you need to be very very careful. So I hope you guys can hear me. If I just show you something, there are a couple of case studies. Out of that whole table that you need to know, there are some stuff which are very often asked. So these are what we call case studies. So very commonly asked. If you do geography, you know case study means very commonly asked. NH4 plus versus NO3 minus. Both of these will give you ammonia gas. But then how do you test for it? You add NaOH aqueous and then you just heat it up and then you will get a pungent gas. So when you are writing observation in practical, yeah, so don't just treat this as alternative to practical. When you go back to the lab, you need to be able to write all this observation down as well. So you get a pungent gas forming, and then what happened is you test the gas because you could smell it. So you have to test the gas. You use red litmus paper. So you always have to specify what you use and what is your result, and then therefore what is your conclusion. Red litmus paper will turn blue, so we get the gas, which is ammonia gas. So you always specify, okay? And then what happened is, what is the ion present? This is your conclusion, okay? These are your observations. Your conclusion will be ammonium ion is present. You don't say your stuff contains ammonia because ammonia is what you give out. Ammonia is what you give out because you have ammonium ion. That is number one mistake that many people have made. They say they get NH3, they say that the solid or the solution contain ammonia. That is wrong. It contains ammonium ion. You don't have to write the equation down, but then sometimes in theory paper, they like to ask you, any hydroxide can take away the H plus because it will form H2O. And then when the NH4 plus loses the H plus, you get NH3 gas. So this is your ionic equation. So I cannot emphasize how important ionic equation is. And then this one gains H plus. So it's acting as a base, it's acting as an acid. Onto the other one, nitrate is a very confusing one, but it's not often asked, but does not mean that they cannot ask you. You see here you have adding NaOH. It's the same thing there. You have to add NaOH, you have to heat it up, but there is something else that's different. You have to have an aluminum foil. This aluminum foil is metal. This is a solid. It is metal solid that you put into the test tubes. Without aluminum All right, sorry, I had to mute Mumtaz there. Anyway, so when we add aluminum foil in the presence of NaOH, when we get NH3, okay, it's actually the test for NO3 minus. You must have aluminum foil, so you will get the exact same thing. What am I doing? The pungent gas forming, and then you get the ammonia gas. However, how can you prove? How can you prove that is NO3 minus is present and not NH4 plus? There is a scenario in a planning question. This planning question says, prove it is nitrate and not ammonium. Because when you have nitrate test, you are adding aluminum foil and NaOH. So if you don't want to be a false positive means it could be, but it's not what you want. So you need to be very, very careful. So how do you address this false positive? So this is a real O-level planning question, so you need to be aware of it. And sometime when we go back to the lab, you experience this, yeah? So NO3 minus give the NH3 and not from the ammonium. How can I prove this? Okay, so the order of doing thing is you got to prove NH4 plus first. You got to remove all ammonia. This is the idea, okay? Remove all ammonia from ammonium first. So what am I going to do? First thing is I will add excess. So you might want to write this down at some point onto your notes, yeah, somewhere, okay? Because you will forget. You listen and you forget. You think about how much you actually gained from me since January and then how much you actually remember, okay? You add excess NaOH, you heat it until no more ammonia is produced, okay? Until no more ammonia gas is produced. How can you tell? Can anyone just tell me? How can you tell when there is no more ammonia produced from this reaction as a result of ammonium reacting with NaOH? Can anyone just tell me? How can you prove that NH3 is no longer produced? So this reaction will produce NH3 because let's say you start from ammonium nitrate. Ammonium nitrate, NH4 plus, NO3 minus. Ammonium nitrate is present in fertilizer. So you have NH4 plus, you will give NH3. I want to remove all the NH3 from NH4 plus. I want to react all the NH4 plus with hydroxide to give me NH3. I want to prove there is no more NH3 produced at the end of the reaction. How can I prove this? Can you just unmute yourself and just shout out if you think you know the answer? Come on, the sooner someone speaks, the sooner we can get through this. Any idea? How can I prove no more ammonia is present? Hello? Anyone? No one? I'm gonna call out a name and see who actually is present. Yeah, okay. Let me see. Yes, Arif. So how can you prove no more ammonia is present or no more ammonia is being produced? You might have to unmute yourself to talk. What do you see? But then we are trying to prove no more ammonia is produced. So when there is no more ammonia given off, what would you see? So it just remains as red. So that means no more ammonia. You expect there to be ammonia. You will see red lemons turn blue because ammonium is present. But then at the end of the reaction, when no more ammonia is given off, that means all the ammonium has been reacted. All the ammonium is gone. All the ammonium ions have reacted. So at that point, then we can be sure no more ammonia comes from the ammonium. Then your second step is to the same solution. So you still have excess NaOH, right? Still have excess NaOH aqueous because that was what you did in the previous equation. What you do now is you add aluminium foil. It has got to be the exact same, same solution because here you have removed all the NH4 plus to form the ammonia. Now I can prove does it contain NO3 minus or not because the NO3 minus will also give me ammonia. If I add aluminium foil with NaOH, if nitrate is present, I'll get ammonia. Because I remove all the ammonia from ammonium, so whatever ammonia I get must come from the nitrate. That's the idea behind this thing. If you know the idea, you can write it in your own words. Then of course we will get the exact same thing, heat it up, we get a pungent gas. So pungent is the smell of the gas. It smells a bit like urine, but it's not the test for the gas. The test is not by smell. You have to test again. The red litmus paper will turn blue. In fact, it's a damp red litmus paper will turn blue. So NH3 is present. The NH3 is the gas that you produce, but what is your conclusion? Conclusion means summary. You are not explaining your conclusion because it's supported by your evidence. Your evidence, which is your observation, is your evidence. Your conclusion is not an explanation because your evidence, your observation is your explanation. Therefore, because I added aluminium foil when there's no more ammonium ions in this second step, since I already used up all the ammonium ions. So the conclusion will be nitrate is present. Okay, this is called qualitative analysis. You are testing for ions. You want to know what ions is present, not what gas is present, but you have to identify every single gas you produce with the test with the result, with the name of the gas as well. Okay, so that's the very first thing I want to talk about. The second thing I want to talk about is this idea, like for example, this question, yeah, you have iron 3 chloride, FeCl3, this is aqueous. Aqueous means it is soluble. I'm just going to find out who hasn't unmuted themselves. Izan hasn't unmuted himself. Okay, that's all right now. All right, now this is a solution. This is a common mistake among a lot of students, yeah. Fe3 plus aqueous versus FeOH3 solid. This is in the presence of a base. In the presence of a base or an alkali, meaning to say you have OH minus. OH minus is hydroxide, is present in base or alkali, and this is what gives you the precipitate, a solid. This is a solution. This is just in water. There is no base in water. Water is pH 7. You just dissolve this in water. So what you have here is a solution. Even though this iron 3 hydroxide is a red-brown PPT, that is not the color of the solution. You have seen this because you actually tested. You tested for the presence of iron 3 plus using a solution of iron 3 plus. You used the solution last time. You did not use the solid. You used a solution of it. And the color you saw last time was ranging between orange yellow to orange brown. It's an orange brown solution depending on concentration. Sometimes it looks a bit yellowy if it is quite dilute. So solution is not a precipitate. A precipitate is not a solution. End of story. Okay. Now I'm going to teach you something. Iron 2 plus aqueous, you also tested this. Before you added the hydroxide or before you added the ammonia, it is not a solid. It is a solution. Solution. Each and every one of you have done at least the qualitative analysis once, except for one person who was absent a couple of times. Okay. Now this solution was see-through. It was not a solid. It was kind of like pale green in color. Pale green solution. It is still colored because it's a compound containing transition metal ion. Iron 2 plus, iron 3 plus, they are compounds of transition metal that give you colored solution. Very, very pale green, not very light, not very heavy color at all. But this solid is a green precipitate, okay? I realize that a lot of people cannot spell this properly, okay? I'm going to spell this slowly. P-R-E, C-I, P-I for P, and then TATE, T-A-T-E. Make sure you can spell this, okay? I've seen a lot of spelling, like percipitate, perpitate, or whatever, percipitate, or whatever, okay? A lot of random spelling. They are all over. You cannot afford to have wrong spelling. These are technical spelling. Precipitate is a solid, and you have got to describe the color. Some of you forget to describe the color of the precipitate. Okay, you cannot just say a precipitate is formed. You must describe the color. We are doing alternative to practical. When you go back to the lab and do actual experiments, it's the exact same thing. You do not say it's theory, you do something different. Practical, you do something different. No. You apply the exact same concept, yeah? So those are the few things that I want to talk about, solution versus precipitate. The third thing I want to talk about is false positive or negative result. So not every result is positive. You are having unknowns. You are trying to investigate. Not every result is positive. There are sometimes you get negative results. Then we will say no observable change. Observable means observable. Okay, let me spell that out properly. O-B-S-E-R, observe, and then verbal. Observable means nothing you can see. It does not mean no reaction. It means you can't see it because either it's colorless or the ions just mix together, but you don't see anything that is worth reporting. This is what we like to use in practical paper. Unless the question specify no reaction, like sometimes they said write no reaction if no reaction. Let me show you. So not in this one, but I think in the second one, they say in the table, write no reaction if there's no change or no reaction. Then you follow the question. Otherwise, you always go back to this, all right? I repeat this again, yeah? We always write no observable change, observable, okay, if we don't expect to see anything, meaning negative result. Here you have iron 3 chloride. Iron 3 chloride, when you see this dilute nitric acid and silver nitrate together, okay, this one first, this one second, it has to be that order. Okay, I'll tell you that in a little bit. This is a test for halide, Halide, halide ion basically is Cl minus, Br minus, and I minus. So what happened is this will give you silver halide. We do not write down our conclusion. Instead, we write down our observations. You never write down conclusion for your evidence, for your observation. You have a chloride. So what you get is you get a white precipitate. Do not ever write PPT unless you are in practical. PPT, which is short for precipitate, is only allowed for practical, only for practical study, which is paper 3 practical. When you're doing alternative or when you're doing theory paper, do not ever write PPT at all. They don't accept that, okay? So a white precipitate forms. Now I tell you sometimes, some students, they just write this, white precipitate. So what about this, okay? I know this is what the table writes, but you are not writing a marking scheme. You are writing to show the examiner you know what you are talking about. You do not want to just, you want to get straight to the point, but you do not want to show them that you only know how to memorize it. You know more than that. You know how to complete your sentence, okay? So this is, well, it's actually correct, but it's not a good type of answer when you're answering or addressing exam questions. The next one is what I want to talk about, negative result. Dilute nitric acid, you add this one first, and then you add barium nitrate. Okay, so this is a test for sulfate. So a lot of people, they write down a white precipitate is observed, a white precipitate forms, because that's what the table gives you. The table of result is a positive result. Table of result always give you positive result. What is the test? What did you add? What is the positive result? You have FeCl3. You have Fe3 plus, you have Cl minus. You do not have sulfate. When you do not have sulfate, that means you have a negative result. If you write down a white precipitate, means you get barium sulfate, but there's no sulfate. So how can you get something if it is not present? That is why I said you need to be very careful. No observable change. No observable change because there is no precipitate form at all. Okay, so just be very careful there. Don't want to mention too much about this. I think in general, people are all right here. Just want to mention about excess. All right, sometimes people write the exact same thing, sort of like red, brown precipitate is formed, or red, brown precipitate forms. And then we don't write again red, brown precipitate forms because it's the exact continuation from the previous bit. So this is precipitate remains insoluble, or precipitate is insoluble. Precipitate does not dissolve. Mention it in excess. Excess of what? Okay, so the next time you do your other work, make sure you do actually specify this thing in excess of what. When you write this thing down, you have to put in the aqueous. It's also to remind yourself later on when you have a table result, is it in NaOH or is it in NH3? Okay, so just be very careful there. Not too difficult there. Oh yeah, I remember what I wanted to say here. A flame test. Flame test is new in your syllabus. It's new in your 2023 syllabus. I told you before, you have seen this with your own eye before, the blue-green color. It's a test for copper 2 plus. Copper 2 plus aqueous, copper 2 plus aqueous solution is pale blue solution. Be very careful. This was what you saw. Copper 2 plus flame test of the cations give you a blue-green color. Okay, they are not the same. This is a flame test. This is a color of the solution. Now you also have copper 2 hydroxide. This is a solid. This is your pale blue precipitate. Okay, now name the gas. I think people can do that. Identify the solid for 2 marks. Your ion is copper 2 plus. This is not copper. Solid N is not copper. It is not pure copper metal. It is not a metal. Okay, it is a compound because when you heat it, you get carbon dioxide. When you heat it, you get carbon dioxide. So just heating. There is no carbonate added, no acid, no carbonate added. So where in the world did you get your carbon dioxide? You get it from your carbonate. So that means you have carbonate. You have copper 2 plus. How do I know it's copper 2 plus? Well, it's copper 2 plus test. The other thing is that it's colored. You see it's colored. Okay, so it contains transition metals such as the copper 2 plus. Combining formula, you get CuCO3. If you decide to use word, make sure you write down copper 2 carbonate. Okay, so I saw Hazwan has a video on. You need to be careful, yeah. Just listening will not help you. You need to really write down some stuff. Okay. Yeah, I could see you on video just now, Hazwan. Yeah, you need to really write down some stuff as I go along. Otherwise, just listening for 1 hour, all of you will have gotten your A star already. But you know, that's not the case. So you need to pick up these little things. It becomes part of your learning process, part of your progress. If you actually write down these notes, these little things eventually become part of your what you have in your mind as you go along the theory. Yeah. So I'm not going to go through all of these. Okay, that is your job to go through the rest. I just want to highlight important details. Yeah. So the next case study is actually on this thing here. So here you will see that to the first portion, add sodium hydroxide until a change is seen. We know that it's not a compound of a transition metal. Some people, I'll show you a mistake. Yeah, this is a mistake. They say L is not transition metal. That is wrong. Okay, that is wrong. I'll tell you why that is wrong. Because the metal itself is the metal. The metal is not the ion. The metal is an element. This is a compound of transition metal, meaning to say when you dissolve in water, does it contain transition metal ion or not? So this one is just forming a colorless solution. Okay, I think some people got confused when it does not contain transition metal ions, you get a colorless solution. To the first bit of this sodium hydroxide, if you get Al3 plus, Zn2 plus, or calcium 2 plus, because you don't know what is happening here. So what actually happens is you get a white precipitate, forms. Okay, I think I just want to remind you, Hazwan, you also have a lot of spelling mistake, yeah, with precipitate. Okay, so you have an excess of aqueous sodium hydroxide. So now you say Al3 plus or Zn2 plus. You do not have that table. Okay, I repeat again, yeah. If you refer to that table all the time, you will never get better at it. You must try and practice writing down that table of results, jumble up the order so that you confuse yourself, so that you are not, rigid. You are not governed by the order that the table give you. Okay, your memory works in such a way that you have to mix them up, like exam questions. Then you will find out, do you know the thing for real, or is all a fake thing? All right. So here you say the precipitate dissolve in excess, or the precipitate is soluble. The precipitate dissolve or is soluble in excess NaOH. We use formula, but we have to write aqueous because it's a solution. And then what do you see? You see a colorless solution. This is important because it's all part of your observations. So here you obviously get colorless solution because it doesn't contain transition metal. It will become important later on when I talk about chromium 3 plus. Now this is our next case study. I keep on talking about case study. Al3 plus versus Zn2 plus. These are very important. How can you tell their difference? Not with NaOH aqueous. You need excess aqueous ammonia. There is the test for it. You need excess aqueous ammonia to differentiate Al3 plus versus Zn2 plus. That is a very popular case study. Okay, so make sure you know that case study means they like to ask you. If you have seen a couple of questions, you know that these are very popular. Okay, so here you get the exact same thing. The white precipitate would form, but then we know that in order to confirm Al3 plus, the precipitate does not dissolve. Okay, the precipitate does not dissolve. It remains insoluble in excess NaOH. I want to remove that. The precipitate is insoluble in excess NaOH. Some people wrote down soluble, so that means they don't know the table because only the zinc hydroxide. When you form the white precipitate, you need to be very careful. This is what you have already. This is your white precipitate versus the AlOH3. This is your precipitate. This is soluble in NaOH aqueous. This is insoluble in NH3 aqueous excess. All right. but zinc 2 plus is insoluble in excess. Oops, sorry, soluble. Did I say soluble or insoluble? Where am I? Soluble in excess, and then OH, and then this is also soluble in excess, NH3 aqueous. Okay, so there's your different case study there. Now onto the other one, the test for Headlight I already mentioned. For that 3 marks, you really need to be careful. There are actually 2 marks available here because you need to add the nitric acid first. I mentioned earlier, why is it the order method? You have to add the acid first because this is a test for Headlight. It's a test for Cl minus, Br minus, I minus. It's the exact same test. You add dilute HNO3, then you add AgNO3. If I use equation like this, I lose the other mark. Why? Because I forgot about this thing called aqueous. This is a precipitation reaction. Precipitation reaction means I have to start from aqueous solution. So the Headlight from aqueous solution, and I will get AgX precipitate. AgCl is white precipitate. AgBr is cream precipitate. AgI is yellow precipitate. All of this is in your paper 3 practical study. If I'm not mistaken, AgBr is new in the 2023 syllabus, and it wasn't out in the previous past papers. It will be out starting from your year onwards, and they can ask you in your theory question as well. Just be careful, yeah? White PPT, cream PPT, yellow PPT. Now, why does this order matter? If you forget the acid, then something will happen. Why do we add acid? This is a common question. Sometimes they do ask you, why? Why we add acid? So this is not what you fill in the table, but this is important. Why do we add acid? You know, acid can react with carbonate. Silver carbonate is actually insoluble. Silver carbonate is an insoluble white PPT. So if carbonate is present, if you don't add this, if you just add silver nitrate, your white PPT could also be this. So this is to prevent false positive. False positive means you are holding someone's life, in your hands. If you are testing if someone has taken drugs or not, and then you forgot the correct test, and then you say, oh, Hazwan has been taking drug, but you forgot the other test that rules out that particular thing. So so it's not right. You have to do this first because acid will react with carbonate. Okay, so to react all carbonate, how do you know no more carbonate is present? No more bubbles, no more effervescence. Of course, if your stuff does not contain carbonate, if no carbonate, then you don't get any effervescence. Effervescence, make sure you can spell it. Yeah? This is stated in the practical sheet. It also means a lot of bubbles of gases. Effervescence, no effervescence with carbonate and acid means no carbonate present. But to rule out any false positive, you always add the dilute acid first. We don't use dilute HCl. Never, ever use HCl. If you put in HCl, then are you testing for chloride or are you just adding chloride to silver nitrate? Okay, that's why we never ever use silver chloride. And we never ever use hydrochloric acid because you don't want to get a false positive for the white PPT. Okay, so when you get iodide, so obviously you get a yellow precipitate. Yeah? That's why I want to say that. The other thing I want to say is to do with barium test, this thing, sulfate. Okay, so I'm all over the place, but today's session is all about highlighting the usual case study. Sulfate is a very important case study as well. We know that barium 2 plus, when you write ionic equation was from a couple of months ago. Just because you're in this class does not mean that you know everything. So you have to recap things on your own. We will not do any revision at all before the end of year. We will not have any revision class before end of year. Okay, revision is all you. Okay, so this is the test for sulfate. Again, we add dilute nitric acid first, dilute HNO3 first, or you can say HNO3 aqueous, and then we add the barium nitrate. Barium nitrate, Ba2 plus NO3 minus, nitrate NO3 minus, barium from group 2, Ba2 plus, so you need 2 of them. Okay, I can use formula if I know what I'm talking about, but I have to write down aqueous very, very clearly. Now we get a white precipitate forming. Now, why in the world did we add the dilute nitric acid first? Because barium carbonate is also insoluble white PPT. So again, for the same reasons, we want to rule out any carbonate, giving false positive. False positive because barium carbonate, if without this barium nitrate plus anything with carbonate, will give you a white precipitate. You cannot 100% say it's sulfate. It can also be barium carbonate because you did not put in the dilute nitric acid. That's why you have to put in the acid to remove all the carbonate. When all the carbonate is gone, there's no more bubbles, no more effervescence. Therefore, any white precipitate that you form will not be from the carbonate because all the carbonate would have reacted to give you carbon dioxide. They already escaped. Carbon dioxide is a gas. Your mass loss will be from the carbon dioxide gas. Okay, so I think that is pretty much it on the case study. Now, actually, one more case study, which is on this question. Chromium 3 plus and iron 2 plus. Very, very famous case study. When you are in the lab, it's easy because the chromium 3 plus has a much nicer green color solution to it. Iron 2 plus is not as deep color. So imagine like the green color of the grass. The grass is a bit greener color. This is a bit darker green compared to the grass. Iron 2 plus solution is not very green. It's very, very pale green. However, we are doing theory. Here it says chromium 3 plus or iron 2 plus. So you cannot identify the browning on the surface. We know the iron 2 plus will turn brown. The iron 2 hydroxide will turn brown on the surface. So this is a solid. So it's a green PPT, green precipitate. It will turn brown on the surface as a result of it going to iron 3 hydroxide. There is just a natural rusting. You know, rusting, when it's exposed to air, it turns brown on the surface. That brown refers to iron 3 hydroxide, but originally it was iron 2. However, chromium 3 plus does not give you that result. That is just something you do in practical study. But here you want to prove that it could be this or this. So you do not put in the second result because that would invalidate. That would mean that you rule out one thing. But here your conclusion, you don't know. This student say he or she does not know if it's iron 2 plus or chromium 3 plus. So you have to write down a green precipitate forms, a green precipitate is formed, something like that, okay? Whether you write down forms or is formed is fine. But then you add excess aqueous ammonia, and you know that chromium 3 hydroxide. So that is actually what is formed because ammonia is also a weak base. Ammonia has a pH greater than 7. When you dissolve ammonia in water, we get NH4 plus and hydroxide. This reversible refer to it being a weak base, but it does give you hydroxide. That's why it can precipitate out the chromium 3 hydroxide and iron 2 hydroxide as your precipitate. So the precipitate is insoluble, or the precipitate does not dissolve. It's up to you how you write. But what is important is you should always try and write this thing down because it's not every time that you will have time to read through the question again. This is for you to read your own handwriting so that you can decide later on what is sensible and what is not sensible. Chromium 3 plus versus iron 2 plus, you have to use, must use NaOH aqueous to differentiate or to distinguish, to tell the difference between the chromium 3 hydroxide and the iron 2 hydroxide. You have to use sodium hydroxide, excess of it, because here you see the conformation. Here you don't see the conformation. So we get a green precipitate forming as well for the first one. But what is important for the second one is, you see there's 2 marks here. Sorry. If you look at your own paper, you will see there's 1 mark here, but there's 2 marks here. Why in the world would they give you 2 marks if you just write down the exact same thing? Which, meaning to say you just write down is soluble. Okay, so you don't get all the 2 marks if you just write down it is soluble. I think I make a mistake in my tutorial video. I missed out one of the point. So you need to really be careful about your point here. You have to write down what you see. You actually did this. you did this practical, okay? You saw this green precipitate, you saw it dissolve. When it dissolve in excess, you will get a colored solution. The question is, what is the color of the solution that you get? Okay, this is soluble in excess, NaOH aqueous. And then what do you see? That is your 1 mark to form green solution. Solution meaning it is not precipitate. Green solution is a compound containing transition metal ion, is colored. So that's the end of that chromium 3 plus versus iron 2 plus case study. Okay, so I hope everyone is clear on this. Yeah. There isn't much question of flame test yet, but I think you will see question of flame test in the work for this week. Yeah, so just be very careful. Onto this one. So you have this question where they say write no reaction where appropriate. So chromium 3 and nitrate, make sure you complete it in excess. What color of the solution that you get? You dissolve the precipitate, the green precipitate dissolve in excess, you get a green solution there. When you see silver nitrate and dilute nitric acid, this is a test for halide. Halide is ions, refer to group 7, chloride, bromide, iodide. So you don't have any halide, so there's no reaction. If this is paper 3, I will write down no observable change, but I know how to read questions because that's what you do when you read question. Aluminium foil, and sodium hydroxide and heat. Okay, so what gas do you get is actually ammonia. I cannot write NH3 because the question specify on name. I think one person in the whole class could not spell ammonia correctly. There was one person, I forgot who it was already. And then you use red litmus paper. In fact, you use damp red litmus paper. Damp meaning moist. So remember, you have to dissolve it a little bit of water. And then what happened is the red litmus or the damp red litmus paper will turn blue. Okay. Now onto the next one. You have iron 2 and you have chloride. I think with hydroxide is okay. One person say like this. Okay. So I'll show you something which is wrong. Yeah. Red brown precipitate is obtained. So red brown precipitate forms. So that one is fine. And then this person say becomes insoluble. Now this is wrong. This is very, very wrong. Becomes insoluble. Becomes mean goes from something to something. But then you already have a precipitate. Precipitate was already insoluble. You need to be careful of your choice of words. English is very important for Cambridge exam. It's all in English, okay? So what you want to say is the precipitate remains insoluble or the precipitate is insoluble, and this is in excess NaOH, aqueous. I know like sometimes marking scheme, they never mention this, but then it's good to put it in practice that you always write these kind of details, yeah? So obviously when you add the silver nitrate and dilute nitric acid, this is a test for halide, you get a white precipitate forming. So a white precipitate forms. Okay, on to the next one. This is a test for nitrate, aluminium and sodium hydroxide and heat. This is a test for nitrate. You do not have nitrate, so you don't have any nitrate, so you get no reaction. Okay. However, you also need to notice that you do have some sodium hydroxide. So some people write down you get a red brown PPT. That is entirely acceptable. That is probably something that you will see. However, in the presence of aluminium and the sodium hydroxide, that precipitate will not stay for long. When you did this in the lab, if you do this in the lab, that precipitate will not stay for long because this and this will undergo a reaction. They can produce you hydrogen gas. Some people have written down hydrogen gas, but that hydrogen gas does not stay around for long. That is the hydrogen gas that you don't test for because that hydrogen gas actually reacts with the nitrate. That is our next topic. As soon as you finish the end of year, we'll cover another topic for year 9, and there will be the end. There will be 33%, which is 1/3 of your O-level chemistry. So we just write down no reaction here because even though you produce hydrogen gas as a result of this reacting with these, it's not something that you test for because it's not the usual reactive metal plus water. It's not the usual metal plus acid that give you the hydrogen gas. So be very, very careful there. Yeah? Next one, iron 2 and iron 3. I remember just now I said the solution originally would be pale green. Sometimes it appear a bit colorless. Yeah. So it's a pale green solution. It's not a green precipitate because this is just without the hydroxide. I think I did something wrong here. It's not red brown PPT. I can't believe no one mentioned it. Yeah, okay. It's a green PPT. green precipitate for iron 2 hydroxide. For iron 3, then you get the red-brown PPT. But as I mentioned, whether you're listening in the background or not, well, I mean, it's really up to you, okay? So this solution contains iron 3. This solution is kind of yellow, orange, brown, depending on concentration is a solution. I don't have much more to say, really. Yep, okay, I have something to say, actually. So when you have this thing here, so you know it could be this, or this, or white precipitate. It dissolves in excess. NaOH could be this or this. It contains NH4 plus. So in your test for NH4 plus, this is a very famous case study. If you see a lot of questions, it comes down to these ammonium ions. But then any gases produced should be identified by test, result, and the name. You haven't mentioned the gas here, but then you know there's a gas being formed. So a pungent gas is formed, or a pungent gas forms. It turns red litmus paper blue. It turns damp red litmus paper blue. You have got to identify the gas always. If you are in practical paper, I assure you, you will get to do qualitative analysis again. If COVID never comes back, if you guys do sit for exams, it will definitely almost certainly be practical paper. I am not a big fan of alternative to practical, because when you go to the sixth form, people will say, have you ever done any practical before? And that is something, a skill that no one can take away from you. If you have done it, you have got to value the time when you did those practical. Yeah. Some students is the next part I want to talk about. Yeah. Some students say here, so L contains Al3 plus or Zn2 plus ion, so there's not a problem. Now this thing here, the precipitate is insoluble in excess. So I have seen this, all right? So what did people write? Yeah? People write down chromium 3 plus, iron 2 plus, iron 3 plus, and Al3 plus. Now that is ridiculous, because you see this is part 1 and this is part 2. To the mixture from 1, it means that this student has not read the question at all. It means this student has not imagined doing the practical himself or herself. To the same mixture, it could be this or this, then I add excess ammonia, then I do not put in extra bit because I do not have that table in front of me. I do not. I follow the logic, the sequence of event from here to here, what actually happened. Okay, so this is the right conclusion, not that, because you already said that a colorless solution, so it does not contain any transition metal ions. That's it on qualitative analysis. All of this, definitely that table, every single test result will never be in your theory paper. That table is not given, but the questions will be in your theory paper, I assure you, okay? What else? Onto the separation technique, there are a couple of things I want to mention. Not this thing here, not this. Yep, onto this thing here. This is on separation technique, okay, separation technique. For 3 marks, these are like essay type of questions. If you do geography, if you do history, you know about essay, you know you need to structure your sentence very, very carefully. Describe means it's not just stating, describe. Explain, describe is not stating. Some people just write down one word, okay? Explain your choice in each case. Sodium chloride is your table salt. You know your table salt is soluble in water, soluble in your distilled water. Sand is SiO2, which is, you know, your white sand. SiO2, as you imagine, silicon bonded to 4 oxygens, giant molecular structure, insoluble in water. Structure and bonding, so every single topic from your topic 1, stats of matter, up until this current topic that we have finished, you've got to go through every single thing in your syllabus. I repeat, yeah, every single statement in your syllabus, in your learner's guide. If you miss it, that means like if I ask it, you can't blame me, because Cambridge already tells you 3 years in advance. Master every single thing in the syllabus. Candidate should be able to, all right? So sand is insoluble in water, insoluble in water. This is your classic primary school. I'm not kidding you, okay? Primary school or lower secondary. You must be able to describe what actually happened. You have a mixture of the solid. So the first thing you do is dissolve or add in distilled water. In our laboratory, you never use any tap water, you use distilled water, and then to dissolve the sodium chloride. But we know sand is insoluble, so sand remain insoluble. If sand remain insoluble, and therefore we can filter the mixture. When we filter the mixture, then sand is collected as residue. Residue, the definition in your syllabus, yeah? The residue is collected as residue. Residue is the solid left behind on the filter. The filtrate contains NaCl, aqueous. Aqueous is not liquid, aqueous is not solid. Aqueous means this thing dissolved in water. You want to get pure and dry. They did not mention crystals. If you do crystallization, it's okay, but they never mention crystals. They just want pure and dry. So what you can do is you can evaporate to dryness because they never mention crystallization here, okay? So evaporate, filtrate to dryness. This is okay here because we did not want to get crystal, we just want pure and dry. To dryness, obtain dry NaCl. So you remove all the water. On to the next one, which is the food coloring from a mixture of 3 food colorings. Some of you have suggested distillation, but you have no information on the boiling point. Distillation works because they have different boiling points. So ethanol, the boiling point I think is around 79 or 80 degrees Celsius. The boiling point of water is around 100 degrees Celsius. Different boiling point. That is very important for distillation apparatus. For distillation principle, you must have different boiling points. You can collect them separately. So this one is definitely using chromatography. But remember just now it does say describe each method. Describe each method. Describe. They don't say state, they say describe. So just by stating, which is probably what the marking scheme will say, does not give you all the marks. Marking scheme is never ever for students. Marking scheme is for the examiner, the Cambridge people, the white people, to mark your paper. They know, they are experts, they are subject experts, just like me. They are looking for you to show them what you are capable of doing. Get straight to the point, okay? Using chromatography, because what is the principle? Because the food colorings have different solubility in the solvent. All right, so we know that how far they move, the different RF value is due to different solubilities in the solvent. So you got to choose a solvent that can, make them move apart. So how do you set it up? So use pencil. So pencil, you got to have different points of interest in order to describe each method, all right? So use pencil to draw a baseline. Baseline is where you started, B-A-S-E-L-I-N-E. This is your starting point to draw a baseline onto which you spot or you spot with the color, with the food coloring, with the mixture of the food coloring, and then place the to draw a baseline on filter paper strip. So this is your chromatogram, filter paper strip. So again, my answer will differ slightly from my previous lecture tutorial. My answer could be slightly different from yours. It doesn't matter. It all comes down to, do you have the points or not, okay? It's really up to individuals to describe their points of interest, all right? Just make sure you prepare your points of interest for each separation techniques so that you'll be able to reproduce it anytime, anywhere, yeah? So place the filter paper into a container or into a beaker, filled with solvent. So you gotta use a solvent. You could use water, you could use ethanol if you want to, but this must be below the baseline. That is your second point, right? So allow separation based on the different solubility, and then work out or calculate RF value, retention values. So from the starting point, the baseline, to where your solute is detected, divided by the distance from the baseline to the solvent front, something like that, okay? Okay, I remember. I need to talk about this kind of situation. This is a planning question, right? So we have a pure carbon, and we also have carbonate. We know that group 2 carbonate, I talk about solubility rules. Okay, so we have around 20 minutes left for the lesson. I really need to cover everything today, because I don't think I'll see you next week actually. So group 2 carbonate is insoluble in water. But then you also know that copper 2 is not group 2. Do you see that how they name the compound? They give this number, Roman numeral, because it is how you name transition metals. You must have this number together with the transition metal to make sense of the Cu2+. So we have CuCO3 there. This includes copper 2 carbonate as well as zinc 2 carbonate. So basically, something which is 2 plus ions with the carbonate, they are insoluble in water. Insoluble in water, carbon is also insoluble in water. Think about your pencil. Your pencil is insoluble in water. That's why you use pencil in order to draw the base lines, because pencil contains graphite, does not dissolve in water, will not get separated. If you use your ball pen ink, ink is a mixture, ink dissolve in water, ink can get separated together with your food coloring, not good for separation at all. So what happens is, when you have carbonate, they are insoluble, your job is remove all the carbonate. You want to react all the carbonate. So the idea here really is react all the carbonate. React all the carbonate. Why? Because when all the carbonate is gone, there will be no more carbonate which is insoluble in water. You can just filter to get the carbon. Now I have acid. Acid reacts with carbonate because this is from your general reactions. Metal carbonate plus acid. As you know, test for carbonate, just now qualitative analysis, carbonate will react with any acid and you get CO2, you get H2O. This is a gas, so you will lose the mass, obviously, as you have seen in a couple of calculation questions from your previous topical test, as well as previous questions. And you get a salt. You will get a sulfuric acid, will give you a sulfate salt. So H2SO4 will give you something that contains SO4 2-. You will get copper 2 sulfate as your salt. Okay, copper 2 sulfate is soluble in water. As you saw, it was the pale blue solution that you used for your qualitative analysis. Some of these are now becoming your chemistry vocabulary. Just be careful, yeah. So what do we know? We do not need a chemical equation because this is just planning. How do you separate the carbon? How do you purify the carbons? Separating the carbons, react the carbonate fully. Remove all the carbonate. So what do? You have to use excess. This term is very important. So you use excess sulfuric acid. Add sulfuric acid in excess to the mixture. The thing is, how would you be able to tell it's in excess? Why is it in excess? Because I want all the carbonate to react, then all my insoluble stuff is just the pure carbon. So what I have then is until no more effervescence or no more bubbles is produced. So there are two observations: until no effervescence is observed, effervescence meaning rapid bubbling, or until no more solid remains. Because actually no more solid remain is wrong, because carbon is insoluble. So carbon will always be solid remaining. So until no more solid remain is wrong. You cannot say that because pure carbon is insoluble. So what happens is you filter the mixture, and then you have to collect the carbon, which is the graphite, as residue. Okay, now you have used excess acid, therefore you have to wash the residue. When you wash it, you don't wash it with acid, you wash it with distilled water. And we know that the carbon is insoluble, but it will wash off the acid. So to wash off the excess acid, and after that you just dry the residue. Okay, you don't want to dry in between filter paper. That's actually bad. If you have seen carbon and paper, they don't mix together. They just stain your paper. So carbon is not a good thing to dry in between filter paper. So you just let it dry naturally on your filter paper instead of rubbing it in between filter paper. This next question is exactly the same scenario. So it's just different, well, 3 mixtures here. That's why it is 6 marks. You need to be careful about how you can get a pure dry sample of polystyrene beads. Polystyrene beads. Polystyrene is this thing called styrofoam. If you have seen packaging materials, these things are insoluble in water. You see, when it dissolves, they will say it dissolved. So when they don't say it dissolve, it means it does not dissolve because it does not mention it dissolve. Okay, so it does not dissolve. So what else can I say? When it reacts, it will say it reacts. It does not react. So this does not react, this does not react, no reaction. So it does not dissolve, but this dissolve and this dissolve. But carbonate, group 2 carbonate is insoluble in water. Group 2 carbonate, which include copper 2 and zinc carbonate, it's insoluble in water. At the moment, if I just filter, I will get rid of sodium fluoride, but I will still have calcium carbonate and polystyrene beads. So what I do is, well, add excess. What acid do I have? I have excess nitric acid. Do I have nitric acid? No, I don't have nitric acid. I can use nitric acid. I can use sulfur. Oh, actually, I do have nitric acid. Nitric acid there. Okay. So nitric acid to the mixture, meaning the hand cream. This is until normal effervescence, normal bubbling. If you don't like the word effervescence, well, you have to like it because there's the term stated in the test for carbonate. So this is to ensure all the carbonate reacts. So now when all the carbonate reacts, you get calcium nitrate. All nitrates are soluble in water. All nitrates are soluble in water. So, then you can filter the mixture. Filter the mixture. Only the beads, only the polystyrene beads are insoluble, and you'll be collected as residue. And just like the previous question, you gotta wash the residue with distilled water because you use excess acid. And here I'm just washing off the excess to wash off the excess nitric acid. And then here, because this is not carbon, I can dry the beads in between filter paper. Okay, because we want pure, so you need to wash it, the excess acid. We want it dry, so we need to dry it. What is important, however, some people have written down crystallization. Crystallization is wrong because crystallization would mean that this dissolves in water. This does not dissolve. You cannot crystallize something if it does not dissolve. This is all stated in your notes, provided you actually went through the lesson, provided you actually went through everything in the notes, and you actually read through more of a textbook. Okay, that is why the next bit is on crystallization. Crystallization is a very important case study. We need to really know how to do crystallization, all right? So we know that we involve mixing two things together. So calcium chloride is soluble, calcium carbonate is insoluble, so you have to mix. This is mixing, so this is your first thing. Your insoluble stuff is going to be calcium carbonate. This is your filtrate. This is your calcium chloride soluble. This is your second step. And your third step is heat. But this is not evaporating to dryness. That is number one mistake a lot of people make. Heating to dryness is not crystallization. Be very careful. If you read these questions, you want to get crystals. Some people just can't read questions. If you want crystals, you have to do crystallization. Crystallization, the last step, is not heating to dryness. Never ever heat to dryness. Instead, you heat until saturated. How do you know the solution is saturated? Now, this is a term which is stated in the syllabus. So this is straight from your syllabus. So if you look back on your notes, we know that saturated solution is a solution where it has got maximum, meaning the most amount, maximum meaning the greatest, the largest, the most amount, you can say amount of solute. I think in the notes they say concentration instead of amount. Is the same thing. So concentration or amount. Solute is important in a solvent. And then this is at a particular temperature, at a given temperature, at a particular or given temperature. So these are all the technical terms that are stated in the syllabus, together with filtrate, together with residue, together with many other things in the syllabus on experimental techniques and separation techniques. So we heat until the solution is saturated. We do not heat until the solid is obtained. Yeah. Saturated solution is a solution. It is not a solid. If you heat until you get a solid, you have gone too far. Okay, you never go too far. Yeah. This is a 3 marks on crystallization. Just like I have written short essays on chromatography, short essays on filtration. Now I'll write a short essay on crystallization. You need to really master this thing, all right? crystals of pure sodium chloride after step 3. Step 3 is basically what I did before. I filter off the insoluble sand. So my filtrate here is just aqueous NaCl. This is not pure. This is not pure because it still contains water. So what you do is you have to evaporate. You have to concentrate the filtrate. Concentrate the filtrate. How do you make something concentrated? You by heating it until it is solutioned. By heating the filtrate until it becomes saturated solution. I repeat again, saturated meaning it's a solution, okay? It still has the maximum amount of solute dissolved in that solvent at a particular temperature. Your second mark will be cool it, allow it to cool. So in order to form crystals, you must allow this saturated solution to cool, and only when cooling, then the crystals will slowly form because you are heating it to the point where the most amount dissolved in it at that higher temperature. When you cool down to lower temperature, then the solubility will decrease and therefore the solid will come out as crystals when you allow it to cool down slowly. After you get that, you need the dry crystals, so you need to filter the crystals. After you filter the crystals, you still have the saturated solution, so you have to wash. You have to wash crystals with cold distilled water. The cold water is very important because if you use just like normal distilled water, you might risk dissolving the crystals again, which really defeat the purpose of you trying to get the dry crystals. After that, you need to dry because they want the dry crystals, so you must have dry crystals that you wash already between filter paper. Okay, so those are like the fixed essay that you can prepare for crystallization there for that 3 marks. Don't want to mention too much about this, but just one idea. This is a hydrated. I just remember in your qualitative analysis just now, there was a solid, and then you heat it, and then you get steam coming off. You get steam, and then you get colorless liquid at the upper part of the tube. This is what you saw last time when I show it to you. When you have a hydrated solid, you will kick out the water of crystallization. So I hope you can see that how all the topics are related together now. This is a blue crystalline salt. It's got a water of crystallization. If you heat it, it's going to give off steam, and that is why they say pure water from this salt, not from your water added. You do not add water to this because if you add water to it, then your water is not from this salt. Be very careful. You want to distill, have this distillation apparatus, but you want to have the solid because when you heat this solid up, you will kick out the water and it will vaporize to steam. And this steam will condense when it passes through the condenser, which you need to fully label where the water goes in and where the water goes out, and you collect pure water at the end. This is related to your qualitative analysis. I think work 1 or work 2, the planning exercise. It says what 2 conclusion can you get? One of it was acidic because it reacts with carbonate to give you effervescence. The other one is that it's hydrated because it gives you steam when you heat it up. You kick out the water of crystallization. It has got water of crystallization. It is a hydrated solid. That was in the qualitative analysis question, yeah? Not too tricky, this one. Actually, this one is a bit tricky, actually. This is, again, obtained crystals. This is dihydrate, so it's got water of crystallization. So what you have to do is you have to use water as your solvent. There is a couple of marks on this thing called extraction. This is something from biology, actually. You will learn this in biology when you do chlorophyll extraction or some other thing. You have to crush up. You have to cut up the leaf and then crush the leaf. You crush it with sand because you are grinding with sand, and this is in mortar and pestle. So sometimes you use ethanol, but here we use water because it depends on what your stuff is soluble in. So we use water here. We use distilled water, and then you have to filter because we just want the filtrate because the filtrate is in water. The filtrate contains the water-soluble acid, and then the crystallizations is exactly the same as before. The fixed assay that I mentioned before, heat the filter until saturated, blah, blah, blah. So sometimes these kind of things you can prepare for. It's a planning, scenario will change, ideas will never change. You just have to, brainstorm your ideas and write down every single detail as much as you can. But make sure you fill in the lines and make sure that you don't overwrite, like sometimes I think Lukman loves to write a lot and then he has all the points, but it defeats the purpose of actually planning before writing. So get straight to the point. That is my point. All right, last thing I want to do was on, not that. So this one was to do extraction and this is just extraction and then chromatography. So 3 marks for extraction, 3 marks for chromatography. Not that. I don't want to talk about that. There was something else I want to talk about. This one. Okay, this is the last thing I want to talk about. All right, potassium sulfate. Trust me, this is the very last thing I'll talk about. I'll try and finish this in 3 minutes. Soluble salt. So you want to get a pure dry sample from the dilute sulfuric acid. Acid reacts to form salt. Acids do not react with salt. I repeat again, acid do not react with salt. Acid reacts with something to give you salt. Acid reacts with metal carbonate. As you know, carbonate reacts with acid to give you salt, CO2 and water. Acid reacts with base to give you salt and water. There's your neutralization. Acid reacts with metal to give you salt and hydrogen gas. Out of these 3 methods, this method cannot be used here because potassium metal is very, very dangerous, very reactive. You will learn more in metal topic, not suitable. If you use potassium in school, I assure you the whole school will explode, yeah? So this is not practical here. Yes, some metal will work, but not for potassium. So you're left between either a base or metal carbonate. You want to start from the dilute sulfuric acid. Because it's a soluble salt, you don't want to use metal carbonate because what you will get is acid is soluble, your salt is soluble, so that's not going to be good because how are you going to, if you use excess acid, how are you going to separate the salt from the acid? Because you want to react all the carbonate, how are you going to separate the excess acid from the salt? So neutralization is going to be the best method I use. So I react KOH, potassium hydroxide, K plus and OH minus with sulfuric acid. So this is your titration. But then we need to do titration. When you do titration, you gotta do with indicator such as methyl orange. So when you have methyl orange is going to be red in acid. It's going to be yellow in base. It's going to be orange at the midpoint with indicator to find out the endpoint. You got to know at what volume will it neutralize exactly. The other thing which is very complicated is indicator is something else you add. If you reach the endpoint, it's ngam, okay, it's chun, that exact volume that get neutralized, but it has got indicator in it. Now we know the endpoint, we got to repeat titration. This is the one that a lot of students didn't get. Why? Why do we need to repeat titration? This is without indicator. If you read the questions, you want pure. We don't want any indicator. But then, without the indicator, we cannot know how much is exact. We don't know how much exactly will react. And we have to react aqueous and aqueous because we are doing titration. One in burette, one in pipette. Make sure you can spell this apparatus correctly. So some people cannot spell them still. So be very, very careful. So now you repeat titration without indicator using the endpoint volume. So I have my exact salt and water being formed and none of excess acid and none of excess base. So I just need to remove my water. They don't mention crystals, so I can just evaporate to dryness. I can evaporate to dryness because they don't mention crystals. But if you want, you can also use crystallization, meaning to say you talk about saturated solutions, the maximum amount of the solute, the salt dissolved in the solvent, in the water, at a particular temperature, allow to cool, and then you filter, and then you wash, and then you dry. So this seems a lot more steps compared to this. When they don't ask crystals, you don't need to talk about crystallization. When they say obtain pure crystals, so make sure you do write about crystallizations. Okay, so it seems like everyone is present. I think, let me just take quick attendance before you leave. And I mean, that's it really for today. So yeah, I mean, if you got any questions, so feel free to just send me a text and ask. But that's pretty much it. You still have 3 more work due Friday next week. I put out all my tutorial videos and all the PDF online, so you can use whatever you want, whenever you want. And yeah, well, that's it for today. It's now 12 o'clock. I'll let you go. Thank you, everyone. I'll share the recording later on the YouTube playlist. Yeah. All right, I'm gonna end the meeting now. Okay. Bye, everyone.